So let me introduce our speaker today, Professor Daniel Liberzon from the University of Illinois at Urbana-Champaign. He was born in the former Soviet Union in 1973 and did his undergraduate studies in the Department of Mechanics and Mathematics at Moscow State University from 89 to 93. In 93, he moved to the U.S. and pursued graduate studies in mathematics at Brandeis University, where he received his PhD in 98. And he was supervised by Professor Roger Brockett of Harvard, which is very well known, as you probably know. Following a postdoctoral position in electrical engineering at Yale from 98 to 2000 with Professor Stephen Morse, he joined UIUC, where he's now a professor in electrical and computer engineering. And he's with the Coordinated Science Lab over there. His research interests include nonlinear control theory, switched and hybrid dynamical systems, control with limited information, and uncertain stochastic systems. He is the author of the books Switching in Systems and Control, which is very related to this topic of discussion here. And the other book is Calculus of Variations and Optimal Control Theory, a Concise Introduction. His work has received several recognitions, including the 2002 IFAC Young Author Prize and the 2007 Donald P. Ekman Award. He delivered a plenary lecture at the 2008 American Control Conference. He served as associate editor for the journals of IEEE Transactions on Automatic Control and Mathematics of Control, Signals and Systems. He's a fellow of the IEEE. And Professor Liberzon was on my PhD committee in 2010, and I took a couple of courses with him too, which I really enjoyed. So please welcome him.
Thanks for the introduction. I should add the last couple of things that you said, Ali, to my biography that I usually give. I think it will enhance my biography quite a bit. So thank you all for joining. I hope that the technology allows you to follow what I'm saying and also will allow some interaction as well, to some extent at least. So I'm going to give, as the title shows, introduction to switching adaptive control, but let me start with a couple of more general remarks. So usually we talk about a plant with an input U and output Y, and we usually see in a continuous classical feedback paradigm a controller connected in a feedback loop to the plant, as shown in this picture. And there are many situations in which this picture is not adequate, and essentially my talk will move us in one direction that generalizes the standard paradigm. And the direction I want to move into is illustrated by this figure here, where for various reasons that I'm going to describe, logical decisions need to be present together with the controllers as part of the feedback mechanism. So in the diagram here, what I'm showing is two controllers. Of course, there could be many more that are connected in feedback with the plant. And there's also a logical unit that supervises these controllers and decides at each point of time which of these controllers is to be connected in feedback with the plant. And there are, as I said, several quite different reasons why one might want to do this. So let me mention a few, even though in this talk I'll basically focus on only one. One reason is just the nature of the control problem itself. There are various control problems that are known that are described by a continuous plant, yet cannot be solved by a continuous controller. There are, for example, certain mechanical systems that cannot be stabilized continuously around an equilibrium, and for such problems, switching is one solution to overcome this obstruction to stabilization. Another area that I've actually worked on, but I'm not going to touch on in this talk, is situations where there are sensors or actuator limitations in the control problem that prevent one from solving the problem in a continuous way, and then again switching becomes the relevant solution. And the third reason is what I'm going to be focusing on here today is situations where the plan has large modeling uncertainty, and so some adaptation is required. And this is the title of my talk is Switching Adaptive Control. In this talk, I'll use switching as a way to orchestrate adaptation, but in a way somewhat different from the traditional continuously tuned adaptive control. And there are also situations where several of these aspects are present, and that gives us even more reason to use switching control as the basic solution idea. So like I said, today I'll be focusing largely on the modeling uncertainties, so on the adaptive control problem, but I should stress that if some of you are interested in solving other problems that may fall into one of the bullets in this list, then many of the ideas that I'll present will hopefully carry over with appropriate modifications to your problems. I'll be happy to discuss these things more if there's interest after I present the material that I plan. So let me first make a bit more precise what I mean by modeling uncertainty or large modeling uncertainty. So what I have in mind in terms of the picture is, first of all, I have unknown parameters in my plan. I'll give specific examples a bit later, but now I want to think a bit more abstractly about the setup. So I have some unknown parameter. I call it little p, that takes values in some set, script p, and this corresponds to one or several unknown parameters in the model of the plan that I'm trying to control. So that's one source of uncertainty, but it's not the only one, because for each fixed value of the parameter p, I also may have unmodeled dynamics illustrated by these little balls in this picture. So I have parametric uncertainty, but on top of the parametric uncertainty, I have unmodeled dynamics, which have to be described mathematically in a precise way. I'm not going to do that right now, but just think of this as a small set of plans centered around a given plant with a given value of p, but there are also some dynamics that do not appear in the models explicitly, but they are somehow small given by some radius, positive radius delta. And in addition to that, I will also have, and so the notation that I'll occasionally use is that I denote each of these balls by FP. So FP will stand for the set of plans close to the given plant with the given value of the parameter P, and then I take the union of these over the set script P that parameterizes the uncertainty. And on top of that, I may also have noise and disturbances that I'll occasionally use in the example. So this is to be understood as a somehow very large set of plants that I'm trying to control. And so unlike some other paradigms that you may be familiar with, like robust control, what I have in mind here is situations where there is no hope that one very smart controller will give us satisfactory performance for all of the plants in the sample. So instead, what I need to do is adapt by learning something online about where in this large family of plants my actual plant is located and tuning the controller parameters online, and I'll do that using switching in the way that I'll describe in this talk. So those of you who have seen adaptive control to some degree would recognize this as basically the standard adaptive control problem. And indeed, that's what I'm studying here. The difference is that in traditional adaptive control, one tunes the controller continuously. So one has a family of controllers suitably parameterized, and one tunes the controller gains, or you may say moves along this controller family in a continuous way based on some kind of estimation procedure. So as new information about the unknown plan becomes available, one tunes the control parameters. It's essentially what I'll be doing here, but the main difference will be that I will not insist on the tuning taking place continuously, but instead I will switch between a family of controllers. So I'll start with a family of controllers, and then again, as new information becomes available, I'll switch from one controller to another. So I'll dispense with a continuous tuning paradigm, and instead we'll have a switching control architecture. And I claim that this is beneficial and lets us overcome certain limitations and obstructions associated with continuous tuning. So those of you who know about adaptive control will see a lot of similarities. Those of you not familiar with adaptive control, I'm not assuming that you know anything about adaptive control, so you can just view this as something developed from scratch, but sometimes some parallels with adaptive control might be useful for just additional insight. So I'll try to use a couple of simple examples throughout the talk to illustrate the ideas. And in fact, overall, the talk will not be very technical. So I can send you to the references for some of the more general developments. But in this talk, I'll try to focus on examples and somehow communicating the main ideas, at least in the first talk. The second seminar tomorrow, for those of you who are interested in more details, will provide a bit more mathematical details behind the design and analysis. Today's talk is largely just an introduction, with most of it being not very formal. So in that spirit, let's look at a quite simple example. So this is a scalar system. You can think of y as the state or the output, so the two are the same. In general, I may use x for the state and y for the output. But here I'm emphasizing that y is the measured variable, so I know y. U is the control input that I'm applying. It's also scalar. It's also known to me. It's chosen by me. The uncertainty in this plant is represented by this number P star, which is unknown. And the only thing I know about P star is that it lies in the set strip P. So this is consistent with the notation I previously introduced. So I take the set strip P to be a union of two intervals on the real line, just to take out 0, because if P star were to be 0, I would lose controllability, I would not be able to influence the plant's behavior. So I just take out arbitrarily a small interval between -0.1 and 0.1. And I also put an upper bound on my certain parameter between -10 and 10. So that's the uncertainty that I'm dealing with. In this example, it's purely parametric. So I don't have any unmodeled dynamics. I don't have any noise or disturbances, at least yet. And let's say the simplest task would be to control to regulate the output of the plant to 0 value. So you can think about first what I would do if P star were known. And this is quite a simple problem. I would be able to just apply, for example, a controller like this, which makes the closed loop system linear, stable, and independent of the parameter. Of course, I cannot do this here because this P star value is not known, so this controller is not implementable. So now I can start thinking about having a family of controllers, each tuned to a particular value of P star. So I'll start first with a possibly large family of controllers, and then as part of my switching control design, I will need to decide which of controllers in the family I would use and how I would switch between them as I hopefully learn more about the star value. Okay, so possibly the simplest choice, but perhaps not the most practical one, is just to go with the family of all of these controllers for various values of P star. Okay, so I have these controllers here that I wrote down, and as P star ranges over the union of these two intervals, I have a continuum of controllers available to me. And I know that whatever the value of P star is, I have one controller in my family that solves the problem. Okay, so I have this controller family here. I use the index Q just to emphasize the difference between the plant parameterization and controller parameterization, which in general need not be the same. But in this particular case, they are the same. So I just have as many controllers as I have possible plants, which is, of course, infinitely many. So if you don't like the fact that I have infinitely many controllers, then I could think about having a smaller controller family that still solves the problem. And if you think about this example for a little bit, you recognize that actually it's the sign of P star that's really important, not so much the value. So if I knew that P star were positive, I would be able to stabilize the plant with just one controller. So I could, in this case, have just two controllers, one for each possibility of whether P star is positive or negative. And this would give me, I will not actually write down for now the formula for these control logs because it's not so important, but you can do it for yourself. And the index set Q that parameterizes my controller family could then be just consisting of two elements, let's say -1 and 1, with the understanding that U1 would have to be designed to stabilize all the plants with positive values of P star, and U-1 would need to stabilize all the plants with negative values of P star. Okay, so this is the first step of the design that you do. Is you come up with a controller family. You may need to go back and refine it later, but here clearly we have a couple of intuitively clear possibilities for what controller families we might want to work with. Okay, so now assuming that I have such a controller family, this slide, this figure depicts the basic architecture of what we call supervisory control or switching control in this context. So I have here the plant with control input U, measured output Y, possibly some internal state here in the plant that's not completely known. On the left side here, I have a family of controllers. In this picture, I choose them to be really a bank of controllers, but if you have some considerations having to do with practical implementations, then you should keep in mind this is just a picture, and it's not necessarily what will actually be implemented, because if you have 100 controllers or actually infinitely many controllers, you will not, in fact, have all of them running in parallel. So I'll explain a little bit later what would be the more efficient way of doing this, but for the purposes of just visualizing this architecture, let's pretend for now that we have these controllers all implemented and running in parallel. And then on the top of the figure, I have a supervisor unit, which I am yet to describe to you how it functions. And the purpose of the supervisor unit is to select what I call a switching signal, sigma. So this will be a function of time, taking values in the index set parameterizing the controller. So to put it simply, at each moment in time, it'll tell me if I should use controller 1 or controller 2, and so on. And it'll be switching through these controllers in a certain fashion. And the purpose of the supervisor is to produce the switching signal. And once the switching signal is produced, the overall behavior of the system is completely described. So essentially, all of the ideas that I will be describing will be focusing on how the supervisor should be run and how it should be analyzed, how one would prove that it functions as intended. Okay. So like I said, sigma switching signal taking values in Q. Q is the index set parameterizing the controller. And then I'll have a switching controller. Sometimes I will denote it by C sub sigma. This is a system that at each moment in time responds to the controller currently in the loop as dictated by the switching signal. Okay, so this is the basic high-level picture, and I'll come back to it and I'll actually fill in some details here and make some things more precise, but that's the basic architecture for us to have in mind. Okay, so now just to make a few general remarks about the supervisory control literature or switching adaptive control literature, there are actually several types of supervision that people have considered. Let me just briefly mention two of them, and I'll focus on the third one in the talk. So when one says that the switching is pre-scheduled or pre-routed, what that means is a simple design where one a priori orders all the controllers, let's say 1, 2, 3, and so on. And then one first tries controller 1, sees whether or not it works. So there is certain falsification criteria or some tests that one runs to see if it does the job or not. If controller 1 doesn't do the job, one switches to controller 2, again, runs a certain testing procedure to check whether controller 2 behaves in a satisfactory way. And if it doesn't, then one switches to controller 3 and so on. So this type of supervision, or this type of switching, actually dates back to early switching adaptive control literature from 1970s and 1980s. It's the simplest possibly to implement, but it also has the worst performance because while you're looking for a good controller, you may spend a lot of time trying out bad ones, and in the meantime, the transient behavior of your plant may be quite bad. So then, in more modern switching adaptive control literature, one moves to more sophisticated schemes, and there's basically two representative schemes that are performance-based and schemes that are estimator-based. For those of you who are somewhat familiar with adaptive control, this gradation corresponds roughly to direct versus indirect adaptive control. So performance-based means that you look at the performance of the controller currently in the loop to decide whether or not to keep it or to switch to another controller. When one says estimator-based, what one has in mind is basing the controller selection on the result of an estimation procedure that aims to estimate what the plant's parameters actually are. So as you receive new information, new estimates about the unknown parameters, you switch on the corresponding controller. So one could argue about the trade-offs between these two approaches. I will not do that in this talk. And I, in this talk, will focus on the estimator-based supervision. And I stress that it's not pre-routed in the sense that I do not know a priori what controllers I will try and discard, but I'll do that online based on estimating the unknown plant parameters. So this brings me to the outline of the rest of my talk. So I will describe the basic components of the supervisor and try to describe the design objectives in a certain systematic way that also connects with how I would in general approach analyzing such systems. And then the more technical part of the seminar, which will most likely fall on tomorrow, will be filling a bit more details about achieving these design objectives. So I will not go into full details, but give certain highlights that will hopefully, for those of you especially interested in this, will let you look at the corresponding papers and understand the details there. So for today, we're staying on the first two, which I'll somehow present together. So describing the basic components of the supervisor, but at the same time, trying to develop intuition about what they are supposed to provide us, what properties they're supposed to have, how they're supposed to function, and how it all comes together when I try to give analysis of the overall supervisory control system. Okay, so let me zoom in on the supervisor unit. I used to have it as just one block in the system, but in fact, I'll decompose it into three smaller parts, each of which I'll describe separately. So the first part is what we call multi-estimator. This is a system that receives as input the signals that are known to me. So these are the control inputs to the plant, and the output Y of the plant. And what this multi-estimator block produces are a bunch of signals. So if Y is the output of the plant, it produces a bunch of signals, let me call them Y1, Y2, and so on, as many as there are unknown parameters. So again, in general, I may have a lot of these or even infinitely many of these. We'll talk later about how to do this more practically, but fixed idea is, let's say I have a bunch of these signals Y sub t that I am trying to produce. And to describe what these signals are, let me also introduce the estimation errors. So think about these signals as trying to be close to the output Y. So closeness can be measured by the difference between the signal Y sub t and the actual output Y of the plant. I'll denote this difference by E sub t, and I'll call it the output estimation error, or just estimation error. And what I want is for these estimation errors to have the property that the one whose index is the correct value of the parameter, I want that estimation error to be small in a certain sense. Okay? So as you recall, I have a parameter t that, t star, that I don't know, that ranges over a certain set that is given to me. And so the t star is the correct value of the parameter. So if I have a certain parameter or parameter vector in my plan model, the t star corresponds to the true values that are there, which are, however, not available to me. And so if I have, let's say, 5 possible values of the parameter, then I will generate 5 of these signals, Y1 through Y5. I will have the corresponding estimation errors, E1 through E5. And I want the error corresponding to the true parameter to be small. So if, in fact, the correct parameter value is the second one, then I want E2 to be small. Of course, I don't know which one of these is the correct one. So this is a non-trivial design problem to design this multi-estimator to have the property that the error whose index matches the correct plant parameter value should be small. So I'll give an example in a minute, but just to think ahead, how we're going to use this is flip this logic and say that if I'm looking at all of these errors and I see that one of them is small, that indicates that the index of that error I'm looking at, that's small, is likely to be the true parameter value. So by turning things around, I'm going to use the size of these estimation errors to do parameter estimation or to attempt parameter identification for my plan. So let me discuss the same example as before. So this design will be quite naive because this example is quite simple. You can refine it and generalize it in various ways, but let's start here. So I have a scalar plan, the same as before. And what I'm going to do is design the multi-estimator in this way. For each value t that corresponds to the possible value of the parameter t star in my plan. So you'll remember that there's actually a continuum of these. So again, this is something that's just a mathematical abstraction. I will write down this scalar differential equation. What I did here is for each p, I copy the right-hand side where p stands in for the unknown parameter. Then I introduce some damping here in the first term on the right-hand side. And what you can very easily show for this multi-estimator is that if you define the estimation errors as before, then the one whose index matches the plant parameter goes to 0 exponentially fast. And the reason for this is that if you focus on that multi-estimator whose index is equal to p star, which is one of the multi-estimators I'm implementing here, then if you subtract and take the derivative of EP star, then terms here will cancel out, and all that will remain here on the right-hand side is negative EP star. So we'll have exponential convergence of EP star to 0, and this is independent of which control signal I'll actually be applying to the plant. Okay, so just a simple observation in this example to illustrate or to give a more precise meaning of what I meant when I said that the estimation error with the correct index should be small. So here small means, for example, exponentially fast converging to 0. Okay. Now, to refine this a little bit, I mentioned that I, in general, want to also allow disturbances present in the plant. So if you add a disturbance on the right-hand side, then if you apply the same multi-estimator design and you calculate the derivative of the estimation error whose index matches the actual parameter value, you will see that you've acquired this additional term. So the disturbance is carried over to the differential equation for the estimation error. And so that means you no longer have EP star converge exponentially fast to 0, but it converges to D. So what that means is if the disturbance is small, then EP star will eventually become small. For bounded disturbance, EP star will eventually become bounded, and so on. And again, this conclusion is valid regardless of what control input I'm applying to the plant. Okay, so now let me go back and address the practical concern that I mentioned, which was that the multi-estimator I'm running here is really a concatenation of infinitely many scalar differential equations, which is not something I would actually be able to implement in practice. So what I would be able to do in practice is actually use this idea of state sharing to run a system of a fixed state dimension that's actually quite low. And this system will be able to generate the same signals that the multi-estimator of infinite state dimension was generating on the previous slide. So let me illustrate how this works. So these were my infinitely many differential equations that generate the signals that I want. So these YPs are the signals that have the right property, that the one with the correct index asymptotically or exponentially tracks the plant's output. Now, since this is not implementable if the index set script E is infinite, the system I'll consider instead will be this one. Okay, so let's look at this. This has two states, which are called Z1 and Z2. It has the same inputs U and Y as the original multi-estimator has. And then it generates each signal YP by this linear combination of the two states Z1 and Z2. Okay, so it still has infinitely many inputs because I actually want to have infinitely many signals available to me. I don't need to have them all together. I can generate each one of them on demand as I want. But the important difference is that the differential equation that I will run, let's say MATLAB, will just have two dynamical states, which is quite different from the original equations, which are not implementable as a finite dimensional dynamical system. Okay, so why does the system do the job? You can just check directly that it produces the same signals Y sub T. And so if you take the Y sub P's defined here as the outputs of the system with states Z1 and Z2, and you differentiate these, and then you use the differential equations for Z1 and Z2. So here I'm just going to plug these in. And then I'm going to recognize that minus Z1 minus T Z2, that is my minus YT. And so it works out, right? You can verify by direct calculation that the outputs of this two-dimensional dynamical system have the same, satisfy the same differential equation as the one I had here originally. And you can see also how I achieved this So what I did is I grouped the right-hand side of the original multi-estimator equations on the top of the slide into two groups, two terms. One is y squared, that's independent of the parameter t, and the second one is p times u, which does depend on the parameter t. And what I did is I put the first one into the first differential equation, and also I have the plus y, which I put there as well. And the second differential equation has this u on the right-hand side, but without the p, and p reappears later when I define the output. Okay, so if I have several different terms depending on p in different ways, I would have to have more states in my system. And then as you do the superposition at the output, you recover the same signal. So for this simple dependence on the parameter, this is quite easy, in fact, to implement this state sharing idea. Okay. So wherever I draw infinite banks of controllers, what I have in mind is that in practice, assuming that the dependence on T is suitable for the state shared implementation, it's the state shared implementation that I'll actually use for my design. But since the signals behave in the same way, for analysis purposes, I might as well use the mathematical abstraction of having infinitely many signals here. For analysis purposes, this makes no difference. Okay, so now having described the multi-estimator, the second block of the three blocks that my supervisor will have is the so-called monitoring signal generator. So it takes as inputs the estimation errors that I already talked about, and it produces as outputs the so-called monitoring signals, mu1, mu2, and so on. And this is actually a very simple idea. These are just filtered versions of the estimation errors. So you don't, in general, want to base your switching logic on the instantaneous values of the estimation errors. You instead want to look at the history of their evolution and define the switching signal based on the history of evolution of the estimation errors. So this is essentially what this block does. It's a filter. So there is no particular one that's set in stone that we have to use, but some examples are, for example, just taking the L2 norm of the estimation errors. So this is one example of a monitoring signal generator. Each mu t at time t is just the integral from 0 to t of the squared norm of the corresponding estimation error. Another way to think about it is that I actually, and this is for us the right way to think about it, is I'll actually run differential equations to implement these monitoring signals. So this is the differential equation. Mu t dot is EP squared norm, initialized at 0. This is what does the integration for me. As you realize, this is not a very good filter to have because it doesn't have built-in stability properties. I can fix that by considering exponential forgetting factor inside the integral, which would correspond to this slightly refined differential equation with the damping given by some design constant lambda that's positive. Again, initialized at 0, this second differential equation will exactly implement this integral with the forgetting factor, and the intuition here is that the second design places more emphasis on more recent values of the estimation error and exponentially discards the past history of the estimation error behavior. Okay, some other examples can be considered, but these two are good enough for our purposes because all I need is certain properties, like if the estimation error is small or bounded, then the same is true of its filtered version, its monitoring signal. It's true for these two examples I have here on the slide. Going back to the same example, this is the multi-estimator that I showed you before using the state shared implementation. And Now, if I want to introduce these monitoring signals, which are just integrals of the square of the estimation error, then I can again use state sharing to make sure that the overall dynamical state of my supervisor has finite dimension. And, well, I write down the formulas here. They may look a bit complicated, but you can easily check that they work. So I take EP squared and I expand it to show explicitly the dependence on the unknown parameter P. It's polynomial here. So I have three terms here that I work with. The first is P independent, the other depends linearly on P, and the last depends quadratically on P. And that tells me that this three-dimensional monitoring signal generator produces the correct signal. So I'll make the slides available after this talk, and you can check this more closely. The main idea here is that if the parameter enters in a sort of separable way on the right-hand side, I don't have some function whose argument is a combination of P and the state. So I don't have something like cosine of P times eta, or here cosine of P times y. That would be a problem. But if I just have some functions of P multiplying functions of the state, and these need not be linear, you see I have a quadratic one here, then this design works. So for quite a large class of plans and quite a large class of corresponding multi-estimators, the state sharing idea lets us keep the dynamical state of the system reasonably low. Okay, and the last element, last block of my supervisor is the switching logic. This is sort of the crucial piece of the supervisor because this tells the system which controller to use at each moment in time. And the basic idea, as I already alluded to earlier, if we look at one of the estimation errors and see that it's small, after we do the filtering, we're looking actually at the corresponding monitoring signal mu of P, and if we see that that's small, then we think that this value of P is likely to be the correct value of the unknown parameter, and therefore the controller tuned to the value of the parameter is expected to do a good job controlling the plan. So this is what this formula reflects. We just take the argument of the monitoring signal. So we take the index that corresponds to the smallest monitoring signal, and we use that index of the controller in feedback with the plan. What is the justification? It's basically what I just said verbally. If the plan is described by this modeling uncertainty, which is the union of small balls of plan centered around certain values of the parameter, and I have the corresponding controllers, each tunes to the value P of the unknown parameter. Then mu P small indicates that EP small indicates the plant is likely to have this value of P as its parameter. Okay, it may not be exactly that plant because of the presence of unmodeled dynamics, but likely the parameter value is the corresponding one. And then if I design my controllers in a smart way to begin with, then hopefully the corresponding controller gives me a stable closed-loop system. Well, this all sounds good, except that it's not quite correct. And some of you who are familiar with adaptive control may recognize the problems here. This, by the way, is something that people call a certainty equivalence principle in adaptive control and also in stochastic control and other settings. What one says is that just use your best estimate at a given time and go with it as if it were the true value of the unknown parameter. As the estimate, as your best guess changes later, you would adjust the controller accordingly. This is what goes sometimes by the name of certainty equivalence. But in fact, the part of the argument that's faulty is this implication here. So we actually only know the converse. We know that if, let's say, P star equals 2, then the estimation error E2 is small. But we don't know the direct implication. So think about it. Maybe the actual value of the parameter among possible values 1, 2, 3, 4, 5. Let's say the actual value is 2, but by coincidence, the error E with index 4 is even smaller than the error with the correct index 2. So there's nothing to prevent false positives here, in the sense that there is nothing to tell us that the wrong estimation error, the one with the wrong index, cannot at a certain point in time become very small, even smaller than the one with the right index. And so, and this is actually a known issue, that this is not how proofs can be constructed, even in traditional adaptive control. It's the same issue that's quite well known. And so we need to look for different ways to organize our thinking and to carry out the analysis. What we need is actually, and this is in traditional continuously tuned adaptive control, this line of thinking, I think, has been pioneered by Steve Morse in 1980s, and it's actually, the work I'm presenting here is based on more recent works of Steve Morse and switching adaptive control. So this is, again, carrying over this line of thinking from adaptive control to switching adaptive control. And the idea that I'm going to propose is, let's just try to bypass this implication and think about what we need. What we need is, if EP is small, then the corresponding controller should give us a stable closed-loop system. And those of you familiar with, let's say, standard linear system theory will recognize that this sounds like a detectability property of the system if we view the estimation error E sub P as its output. So there is some detectability property of the system lurking behind the correct analysis that we're looking for here. Let me give you a brief reminder of the detectability. So for the linear systems, let's say I have this linear plant, which I think of as my unknown plant in closed loop with a Q controller, P sub Q. And so I have Q as the index here. And I view the corresponding estimation error as the output. If I want the system to be detectable, what this means, one of the equivalent descriptions of detectability, is that whenever the output converges to 0, the state will also converge to 0. Equivalently, as is well known, hopefully most of you remember, there exists an output injection matrix, L, or L sub Q, because everything is indexed by Q, such that the corresponding matrix A minus LT is Hurwitz. Okay? And the way to see the equivalence here is that if such an output injection matrix L makes A minus LT Hurwitz, then I can rewrite the plant in this way by just adding and subtracting LCX, which is the same as LE. And because this is asymptotically stable, I recover the property that if the output E sub Q goes to 0, then the state goes to 0. So this is just a quick refresher on detectability. And now going back to the supervisor, if roughly the switching logic wants to pick the index of the smallest monitoring signal, this will hopefully guarantee that the switching estimation error, E sub sigma, is small. So what the previous discussion ignores is the fact that there is persistent, in general, persistent switching in the plant, in the closed loop system here. And so what I need to do is refine my thinking to really capture this implication, that rather than having detectability for each frozen index of the controller, I need the overall switch closed loop system to be detectable with respect to the estimation error that switches according to how the controllers are placed in the feedback loop with the plant. Okay, so this would be switch detectability. I need to go back and sort of rethink slightly the detectability discussion that I just gave. So what can I say about detectability under switching? Let's now have a more realistic situation where I have a plant in closed loop with a switch controller. T sub sigma. So sigma here is a function of time. I don't write it as sigma of T, but that's what it is. And I also have the corresponding output that switches between the different estimation errors, or switches between different T matrices. That I take to be the output of my plan. And I want the system to be detectable in the same sense as the standard detectability suggests. Okay? I'm willing to assume that for each frozen value of sigma, that is, for as long as the controller in the loop is fixed, I have detectability, because that's what I already discussed, and it's somehow clear that that is a starting assumption that I should have fulfilled. Then if I use the corresponding output injection matrices L sub Q, but now for different values of Q, now the switched version of the previous discussion, then I need this switched system, switched linear system, to be asymptotically stable. Okay? So there is, in fact, a lot of literature on stability of switched linear systems. This talk is largely based on the last chapter of my book that Ali mentioned when he was introducing the beginning book called Switching in Systems and Control. And in the earlier chapter of that book, you can find the background information about stability of switch systems. Just to mention a couple of very basic facts that many of you might have already seen somewhere, is there are certain classes of switching signals that are known to be non-destabilizing, in the sense that if you start switching between stable systems, you will maintain stability. It's not always true. Switching can, in general, destabilize an otherwise stable system, but if you switch carefully enough, this will not happen. Careful enough may mean one of the following things. If switching stops in finite time, that's clearly a very simple and desirable case. If you switch for a while and then you just stop switching and you follow from that moment on one of the subsystems and you assume that that subsystem was asymptotically stable, then of course asymptotic stability will be preserved. Even though this is a very simple case, it will be relevant to us because, and I'll tell you later, tomorrow, under certain conditions for the supervisory control design that I described, the property that switching stops in finite time can actually be shown, at least under some idealized conditions. If this cannot be shown, then what you typically do is try to restrict the speed of switching. You try to show that your switching signal is slow, at least in certain average sense. Again, I'll have to make that a bit more precise tomorrow. And then if you switch slowly enough among stable systems, then stability is not compromised. So these are the types of things that we'll need to see present in our switching signal. And because the switching signal is produced by the supervisor, these are some of the design guidelines that the supervisor will have to go by. Okay. So I am basically almost at the end of the first hour of my talk. And what I want to do is give you a summary to organize a little bit better some of the properties we already noticed that our system needs to possess. And then I will not tackle today the question of how these properties are to be enforced in a more systematic way, but that's what I will be dealing with in the follow-up seminar tomorrow. But the summary of things that I already mentioned during today's lecture, first, at least one of the estimation errors, namely the one with the matching index, with the index equal to the actual parameter value, must be small in a certain sense. The block that must ensure this is the multi-estimator. We considered an example where, for a simple scalar plan, we could see that this can be achieved also in the presence of disturbance if you interpret small in an appropriate sense. Okay, so this is a summary of what we saw for that example. The estimation error approaches zero in the absence of noise disturbances on model dynamics and is bounded for bounded noise and disturbances. The second property that we have mentioned as well is that for each fixed controller, the corresponding closed-loop system should be detectable with respect to the estimation error E sub q viewed as the output. So this is before you start switching, just the frozen controller in the loop has to provide this detectability property of the system with respect to this auxiliary output E sub q. And this is what the candidate controller choice will have to guarantee, because this has nothing to do with switching, nothing to do with the estimator. It's what the candidate controllers have to give us. And then for the switching logic, we noted essentially two things that we expect from it. One is that the estimation error E sub sigma has to be somehow bounded in terms of the smallest of the estimation errors E sub p. If this sounds a bit cryptic, I'll try to make more sense out of this tomorrow, but this is what we had in mind when we said at each moment in time we're going to pick the index, the controller index corresponding to the smallest estimation error, because we want to keep E sub sigma small. And finally, the detectability property should be preserved by the closed-loop system. So the switch closed-loop system should be detectable with respect to the switch output, provided that this is true for every frozen value of the switching signal. Okay, so these two properties are to be enforced by the switching logic. And if you think about them for a few minutes, and I'll discuss this more tomorrow, and you have more time to think about it perhaps until then, these two are in fact conflicting, and this will present the main challenge for us moving forward, because for property 3, we want to switch to the smallest monitoring signal right away. So whenever the one I'm using is no longer the smallest one, I want to immediately switch to another one that's smaller to maintain property 3. But on the other hand, as I just mentioned a minute ago, for detectability to be preserved, which is closely related to stability of the output injected system being preserved, I want to switch slowly, or hopefully after a while not switch at all. And so how I reconcile these two will be the subject of a bit more scrutiny tomorrow. Excuse me. And finally, now glossing over this challenge and assuming that somehow I was able to enforce all of these 4 properties by properly designing my various parts of my system, the analysis, at least in a nutshell, is quite simple. So the analysis will be that 1 and 3 will guarantee smallness of E sub sigma, right? Because from property 1, I know that some fixed estimation error EP star is small, and then property 3 will guarantee that the switched estimation error is also small in a certain sense. That's roughly the kind of conclusion I'll be able to draw. And properties 2 and 4 combined will imply detectability of the switched closed-loop system with respect to the switched output E sub sigma. And then just it remains to recall what detectability means, and it means that these two together imply that the state is small, and this will roughly be the end of my analysis. Okay. So what remains for us to do is to make these properties, which are stated here very loosely, very informally, somewhat more precise, and talk about how they can be achieved. The good thing about this design is it's modular in the sense that each property has a specific block of the system responsible for it, right? So one of you could go out and design a multi-estimator with property 1 in mind. Another one of you could go and come back with a family of candidate controllers, guaranteeing property 2, and so on. And when we put the design together, the analysis should follow through as explained at the bottom of the slide. So there is not any interconnection between the different properties, except properties 3 and 4, as I mentioned, are intertwined because the switching logic is supposed to strike a balance between them, and that's something we'll need to look at in more detail. What I'll do tomorrow is talk about how the switching logic can provide these properties 3 and 4, what switching logic specifically can do this. I'll also talk about how one might go about providing property 2, what tools are available for designing candidate controllers, guaranteeing property 2. I will not talk a whole lot about property 1 beyond what I already mentioned by way of simple examples, but there are some references in the literature I can provide that go further in this direction. But my focus will be on properties 2 for the candidate controllers and 3 and 4 for the switching logic. So I believe I have to.
All right. Can you hear us?
Yes?
Yeah. So, are there any questions for President?
I do have quite a few questions.
Yeah. You want to step down to the microphone? So maybe.
Basically, I have maybe about 7 questions actually. First one is, how do you select the number of estimators? Is there a systematic process for that? The second question is, how do you do that if you have multiple parameters in multiple dimensions? How do you handle the disturbances? One of the things that he had was that EP star was tending to D, right? So is there I guess you could have some disturbance cancellation type schemes or the feed forward type of schemes. What if the P is not in the linear form? How do you reduce the transient effects to go from one sigma to another sigma? So for example, can you do some sort of like a soft max type of approaches? And what are the other ways that you can approach this supervisory control? So maybe either you can address it today or tomorrow, that's fine.
Okay. So I think your first question, if I heard you correctly, is how I select the number.
Yeah, because you're right. Yeah, you had the whole continuous region you had. So one good thing about it is that I really like your state sharing approach, which enables you to compute things very quickly. But is there a process that you have, like maybe some clustering or some sort of grouping things? Or is it still experimental type of work on real systems?
Yeah, I don't think that I have a very general answer to this. So I think the most relevant example was this one that we looked at, where you have this. So first of all, the script T, let's say, is given to me because this is some calibration of parameters in my model, which tells me that these are the bounds that I know the actual parameters will fall into. And then the question would be how many controllers, so the first question, I guess, how many controllers I would actually pick from my controller family. So here I indicated 2 sort of extreme choices, right? One is I choose 1 controller per point in my parameter range, which will definitely be enough, but will be somehow too many for implementation purposes. The other, I didn't write this down, the formula for the case where they have 2 controllers, but I believe that I can write down a controller to have 2 controllers that will stabilize, 1 for positive, 1 for negative T star. And then you may ask, well, what kind of performance do you expect, right? So if this controller is tuned for a parameter value equal to, let's say, 5, then it doesn't give very fast convergence for parameter values closer to the boundaries of this interval. So then, sort of on a trial and error basis or guided by your performance criteria, you would add more controllers. Maybe you would have 5 on the right side and 5 on the left side. So this is something I would say that has to be done on a case-by-case basis, so that the baseline performance of the candidate controller is in line with your specification. Then what my results will do is they will characterize to what extent the performance is preserved once you start switching between these controllers. So for that, I will have certain quantifiable bounds. And so maybe you can repeat your second question to make sure I get it correctly.
This is multi-dimensional.
Right. So,
yeah, the parameter space is multi-dimensional. Like in this case, it was just a scalar thing. So are there any systematic processes for, say, 10-dimensional space of the parameters? You know, so.
Right. So again, so there's a couple of having to do with dimensions. One is that I assume that actually all of the controllers, I think I tacitly assume that all of the controllers have a fixed state dimension. So if that's not the case, I could always embed them in a state of one dimension that's large enough to capture all of them. So for the parameter, if it's multidimensional, I mean, this will go through without any problems. I just have to, again, do some gridding on this high-dimensional space to choose my family of controllers. And as I said, there aren't very many general results, but I can point you to a couple of papers that, under certain assumptions, characterize robustness regions. They have to play with the robustness regions for each controller to decide, how many controllers you have to put on this large dimensional compact set, let's say, that parameterizes your plan, so that their individual robustness regions cover the whole thing. And then again, you have to see by how much the robustness gets reduced as a result of switching. So that's something I'll be able to comment on.
How do you handle disturbances is the third question that I had.
Yes, so far, all I said about the disturbance was what I know about the estimation error. That if we go to the last slide on which I stopped today, let's say this one, so I know that what I need from a multi-estimator is that if I have a bounded disturbance, then the corresponding estimation error should be bounded. This is something that's quite reasonable. For linear systems, there are general results, because this has little to do with switching. This is something that has been worked out in the context of classical adaptive control. So there are some results that would tell you that you can pick estimators that guarantee this. And then what I'll talk about tomorrow is how, for this case, the switching logic will guarantee switching that's slow in the average dwell time sense. And via that idea, I'll be able to prove stability, where stability of a closed system will mean, of course, not converging to zero, but convergence of the state to certain range of values that's commensurate with the size of your bounded disturbance.
Yeah. Then what if this P appears in non-linearly in the dynamics? Is the next question that I had.
Right. So this would be an example.
In that case, is it? Oh, looks like.
I think there is some issue with the video.
Okay.
It will pick up. I think you can hear us.
Okay. I guess for the nonlinear case, what do you do?
So are you asking about the dependence, nonlinear dependence of the right-hand side on the parameter, like here? Or are you asking about something?
Yeah. Basically, you will have maybe, say you have like PUY or something like that, So
that's not going to be a problem as long as I can separate. So as long as I have something like a function of P times another function of my system variable, this will work as on the slide. I'll just forget temporarily the function of T. I will put the other function of my system variables on the right-hand side of the state shared implementation, and then I'll post-multiply by the function of P at the output stage. So if this, for example, p squared was any other function of p, that would be okay. But if you, as I said, if you take this p squared d2 squared and you put that inside some function like a tangent, then this design will break down. So in that case, you better have finitely many parameter values, because if you have infinitely many or too many to implement the system with the corresponding state dimension, then the state sharing idea would not be useful. So one of the limitations here is that the dependence on the parameter has to be nice in the sense that it can be separated into a product of something that depends only on the parameter and something that depends only on the system variable. Now, if you look at the classical adaptive control textbook, they actually almost always require more. They require the parameters enter linearly, because then they can develop the parametric models on which usual estimation schemes are based. So this is sort of, this relaxes, what I have here relaxes the standard assumption, but it's still quite restrictive. And if you give me a very general dependence on the parameter, then I would probably come back and say that your parameterization is too unfriendly for my design to work.
How do you reduce this transient effects? Is that like in the PID thing, right? We switch very slowly, like we do things like velocity, feedback, that kind of things, right? Like delta stepping.
Right.
Do you have something similar in this context too for supervisory control when you go from, say, one sigma to another sigma?
Right. So
have it so like jump in your errors.
Yeah. So the worst thing that from the designs that exist, the worst transient performance would be actually, as I mentioned, when the search is pre-routed, when I don't react online, but rather have a preset sequence. So I would say that in empirical observations, when we run simulations of this design, the transient performance here would be much better than for the pre-routed searches. Now, on the other hand, as far as having hard results on the transient bounds, this would have to be on a case-by-case basis. And I don't think we have very general results. But I think also in adaptive control, this would be largely an open problem for general plans. So I could say empirically that the transient behavior would be related to the parameters of the switching logic, which I haven't yet spoken about. So that I have certain design parameters in my switching logic that I'll talk about tomorrow that can be tuned to achieve transient behavior, but this is more example by example based.
Yeah, maybe if you could also talk in general about other ways of doing supervisory control tomorrow, that would be nice. Like
about other ways too.
Yeah, like maybe the people from DEDS, discrete event dynamic systems people, they talk about supervisory control, so, and
more sensor-based rather than parameter-uncertain.
right, one of the discrete end of things.
Right. So yeah,
just give an overview of, so that other people get to know what are the other ways that people can approach supervisory control. But
right.
Your talk was excellent. You're a very good teacher. You can see that.
Thank you. I'd be very happy. In fact, for tomorrow, I think the format that we had in mind would be a bit more open-ended, with people asking me questions maybe before tomorrow's seminar based on what they heard today, and also at the end. So I may not have, of course, prepared slides on other approaches, but I'll be very happy to have an open discussion about comparing what I presented here with some of the other things that you may have in mind. Sure.
I have a question.
Okay, Ali.
So back to the multi-estimator that you had, if you can show that slide.
Multi-estimator, this one?
And then the block that generates the mu1 through mu p based on the error readings, so after the multi-estimator. So you gave an example, the slide before that. You gave an example so the mu p example that you're giving here is followed by the argmin that generates your sigma, right?
Correct.
So what I'm thinking of is, what if your EP is always biased in terms of a large value for, let's say, one condition, and then once you switch to another controller, then this EP is smaller now than the other, let's say E2 or E1, but the problem is your history of EP is going to dominate mu P. Or vice versa. So there is, if you use something like what you're showing here, which is the integral of EP, the L2 norm, then your history might affect your next decisions with your argmin. Is that something that needs to be reset somehow or to be considered somehow?
Right. I think I understand the question. So one thing I should say is that the argmin is not going to be the final form of the switching logic. We're going to refine it because argmin might actually lead to very fast switching, and it's not going to be good enough for my analysis tools. So the argmin is going to be the basis, but then we're going to refine it by essentially sampling it. I'm only going to switch to the smallest index every now and then in a certain sense. Now, to more precisely to answer your question, what's going to happen is two things. Either eventually the right estimation error will become smaller, and I will eventually, maybe after some delay, latch on to the correct index, or something that you described would happen, which is somehow be continuously fooled by, say, the wrong estimation error. So this may, in fact, happen. So the scenario that may very well happen is that I have, let's say, the correct index is E2, and I have E2 that is small in a certain sense, but E1 is even smaller. And I look at this integral, E1 continues for a while or maybe forever to be smaller than E2. And what my switching control will do is just use the controller with index 1, which is the wrong controller, so to speak. So the bad news is that I will never identify the plan parameter correctly, because I'll continue to think that my P star equals 1, even though in fact it equals 2. But I never actually said that I'm after parameter identification, right? All I'm trying to do is stabilize the plan, and the plans will still be stabilized, because in this scenario, I mean, it's somewhat unlikely, but it can happen. E1 is small. I'm using the first controller. The first controller provides detectability through E1. So because of that, and the fact that E1 is small, my state will converge. So in the somewhat unlikely scenario that we're describing, the parameter identification will not occur, but stability will still occur. So this wrong controller will somehow still stabilize the plan, because if it doesn't, the only way it can fail because of detectability is that E1 will, at some point, will need to spike up. And when that happens, I'll switch away. If this never happens, that means I'll be continuously somehow fooled by E1, thinking it's the right one, but the stabilization will not be affected by this. Let me know if it doesn't make sense.
Yeah, it does make sense. So, any other questions?
Also, I think the forgetting factor that you added, that would also
the exponential factor.
Right.
That will make the finite.
Yeah. So one last question is on the possibility of having a kind of skipping the monitoring signals generator and using your errors into the argmin option, or even if it's something that's smoother than the argmin. How can you elaborate a little more on not using the error directly? Because for practical applications, it might be reasonable to have something that's faster in terms of actuating which sigma you want.
Yeah, but you don't want to based on one sample. So what is the basic?
It's smoothing out, taking the history.
So you can say that by selecting lambda, you could be making faster decisions, right? So if you make a lambda,
I think that you could envision just, let's say, setting mu p equal to EP, if in your problem this makes sense. And I think I'd have to follow through the analysis, but I think this will not really affect anything. have a disturbance, the filtering properties, I think, are useful. If you have, for example, the decaying L2 norm here would somehow smooth out the behavior of ET, which may have large spikes due to the disturbance hitting. And so this may, if you don't do that, that would mean that your switching signal reacts in a very fussy way to spikes in the estimation error caused by untypically large values of disturbance. I think from the point of view of having a better performing system, this filter is beneficial, but I think if you want to remove it, I imagine that it's not really necessary, right? So if you're happy with just using estimation errors for the switching logic, I think you can show similar results.
I guess it comes down to really how good are your estimators and how much you trust your estimation error and process.
I'm sorry, I didn't understand the beginning of what you said.
I'm saying it comes down to basically how much you trust your estimation stage and how good are your estimates really. Yeah.
Right, okay. Right. So you want to avoid, because typically the correct estimation error will eventually become smaller than the other one, and so you want to avoid following the wrong one and then jumping back and forth, reacting in a very sort of fussy way to them crossing each other. So the filtering will somehow smooth over. You will typically see fewer switches, and the stability properties of the system will still be correct.
So maybe for tomorrow, one good strategy, since we're going to have more open time, is if anyone in this room would like to get an example or something that they wondered about after this presentation, and then we can have it as an example that we solve together, more like a...
That's what you guys should have done by now, by contacting UTC. I'm talking about the supervisor.
No, we shouldn't, because UTC wasn't really involved in the preparation process for this.
No,
but,
so that you guys can respond nicely on that RFP.
Yeah, we can show some of the examples that UTC is interested in and see how they apply here.
Yeah.